Hey, hello everyone. Welcome to the lecture for MRI, the Basics, Chapter 18, which is all about artifacts in MRI. So there's a bunch of different artifacts we can encounter in MRI, a few of which I've seen already, and I've tried to annotate that here, but a number of new ones that we'll introduce in this chapter. So these include aliasing, off-resonance displacement artifacts, boundary or partial volume effects, truncation or Gibbs ringing artifacts, motion artifacts, a magic angle effect, RF crosstalk, RF zipper artifacts, T2 star artifacts, a couple of gradient related artifacts, eddy currents and gradient non-linearity, and then data errors like the spike artifact, and finally dielectric effects, so image shading. So this is just a refresher or review on aliasing, but just a reminder that aliasing is going to happen when our phase encoding field of view is too small. So I've already annotated on these images which direction are the phase and frequency encoding, as you've seen in the example we did together. And the solutions to this type of artifact increase the field of view in the phase encoding direction. Sometimes there's an option called, quote, no phase wrap. What this is actually doing is actually doubling the field of view in the phase direction and then just not showing you half of the field of view in that direction. So it increases the scan time. The example illustrated at the bottom, which we're going to go through more detail through chapter 25, are using what are so-called outer volume suppression pulses to eliminate the magnetization from certain regions. Okay. The next concept we want to go through here, because it's a source of several very common artifacts, are off-resonance effects. And what generally we mean by off-resonance effects is that something that's creating a change in the magnetic field and therefore the resonance frequency. And they're primarily due to three sources. The first is main field or B0 inhomogeneity. This is typically something on the order of 1 ppm or 1 part per million, simply because we just can't make a perfect main magnetic field. The second source are differences in material magnetic susceptibilities. So there are changes in the magnetic field at the boundaries of materials, and the most common of those in MRI are boundaries between tissue and air, as well as with metal maybe present from implants. And then the third source that we're introducing here in this lecture is chemical shift. And this is specifically typically a 3.5 part per million shift between the resonance frequencies of fat and water. And since we rely on frequency so much, for example, for frequency encoding, RF pulses, among other things, when you have these unexpected deviations in the magnetic field, they lead to artifacts. So I want to go through both magnetic susceptibility and chemical shift here. And this is from an earlier lecture, but a refresher. We're using this the Greek symbol Xi for this, and there's both diamagnetic, paramagnetic, and ferromagnetic materials. Our tissue is primarily diamagnetic. Paramagnetic materials include iron or gadolinium, contrast agents, oxygen as well. So when we have and even air annotated here. And ferromagnetic, of course, things that are attracted into the magnet, so should not be present at all in any imaging experiment. And these materials, when they have there's differences in magnetic susceptibility, there's a boundary effect, and I'll illustrate that in a few slides, that'll cause local changes in the magnetic field. Then the other major source of off-resonance is chemical shift. And so chemical shift is defined as changes in resonance frequency due to differences in molecular structure, which is the basis of all NMR spectroscopy, powerful technique for interrogating the molecular structure. In MRI, it tends to be more of a either causing artifacts or sort of a feature. And we make, there's only two basic molecular structures that have a significant impact on MRI. The first is what we are typically imaging, which is protons and water molecules, which by NMR standards are defined to be at 4.7 parts per million. And the other source of protons are from lipids. And what the spectrum here illustrates is there's multiple resonances from the different groups present in lipids. We typically make a simplifying approximation. You can see the methylene peak is the largest, the Ch2, and so we typically assume that the overall chemical shift of lipids in the body is at the NMR reference frequency of 1.2 parts per million. And this means that we have basically this is where this value 3.5 parts per million comes from. So we have about a 3.5 part per million shift between our primary lipid resonance and our water resonance. Okay, so how does this affect imaging? The first example we'll go through here is what I'm going to call displacement artifacts. And due to our different sources of off-resonance chemical shift or magnetic susceptibility. And really the core of the issue here is we're trying to use frequency to encode location in one dimension. That is our frequency encoding. But if we have off-resonance fundamentally changes the frequency to be not what we expect in our typical frequency encoding experiment. And so we get shifts in the image in the frequency encoding direction. And we can divide this up into both the chemical shift displacement and the magnetic susceptibility displacement because they have slightly different characteristics in our image and that we'll go through. So first off, chemical shift, which there we're referring to not water. So chemical shift is typically referring to frequency shift from fat. We're going to get this displacement in the frequency encoding direction. And we can have this effect, for example, that fat, because it has a different frequency, it may at a different location, it will actually appear as the same frequency as a different location from water. And I'll illustrate that more clearly in the next slide here. And what this shows in the image is some examples of what this appears like. You can see these bright bands that are not real. They are just the overlap of these signals in the image. And also these dark bands. So whether the fat and water signals have overlapped with each other or they've been separated from each other. And there are a couple of solutions to this. The bandwidth, which we'll see, is the way to, increasing the readout gradient amplitude, and then a couple of other techniques that are covered in chapter 25, fat suppression or fat water separation. Okay, so here I'm going to create an example here of a simple object. Let's just say looks something like this, where it's two compartments here. The and for the purposes of this example, say the inner compartment here is fat, and the outer compartment here is water. Okay, so this is water. The center here is fat. And let's draw on here. So we're going to be doing illustrate what's happening during frequency encoding. We're going to have this relationship, and now I'm going to specifically annotate this with the color of water, where what we expect from frequency encoding is that the frequency, and now I'm going to annotate this as the frequency of our water protons, is equal to gamma bar times our readout gradient amplitude times position. And this says our frequency here for water is 0. But what happens for fat? Fat has an overall frequency difference of, we'll call this delta F fat. Just has a fundamental shift in the resonance frequency compared to water. So the effect that that has on our frequency encoding in this perspective is it shifts our line here. For fat protons as a function of position, it's going to be equal to gamma bar times our gradient readout amplitude plus this offset. This is the, and this is what we would call as the chemical shift here. There's some frequency offset from water, and that's going to get mixed up into our image. So let's look at what our normal imaging problem would be. Say we look at some points here in our water at the edges. These points in X are going to map to these frequency values. And then when we do our reconstruction, we're taking this frequency axis and we're converting it back into X. Okay, so we use our relationship of the gradient and we say, okay, the frequencies we get map back to these positions. And we will, frequency encoding works in this case. This is what we've gone over before. Now where things get disrupted here is for our fat. If we can illustrate this. So if we, for example, look at these three locations in X, and this is only a frequency encoding issue, in fact. We're looking at these three locations, but now the frequencies at these locations are going to follow this yellow curve. So they're the effect of the gradient plus the addition of this off resonance term here. Okay, so when we take this, now what I've drawn here is that these points in space, the orange points, are mapped to frequency by the yellow points. So then when we look at the frequencies we get in the signal, and we follow this mapping back to our image, you can see that our original locations are going to be shifted because they are now represented by a shifted set of frequencies. So they would actually be mapped to these points, right? And so again, look along this frequency axis in the middle. Look at these black circles. Those are the locations of our water, our reference locations, what we know. And then the frequencies that we're getting from the fat component of this object are the orange circles here, which you can see are clearly shifted from the actual location of the object. So what we're going to see overall is this type of shift where our where there's this, and this is the chemical shift displacement artifact, would be, I can sketch it up here. Some shift in X of the lipid component here. And can actually derive from that relationship there that it's going to be proportional to the chemical shift frequency difference of fat from water divided by gamma times our gradient readout amplitude. Okay, so that's the difference, the amount of the shift there. We can determine that based on our readout gradient amplitude and the frequency shift of fat. We can also reformulate this, for example, in terms of spatial resolution and the field of view as well. Okay, next I want to examine what types of artifacts we see from displacement due to magnetic susceptibility differences. So how we're going to set up, let me look at this, is we're going to create a tissue boundary here, an air tissue boundary. Let's say on one side here we have tissue, and the other side here we have air. So one side being diamagnetic, the other side being paramagnetic. Okay, and what this means is that there's a change in the Z magnetic field right at the interface. And the sign of this change depends on the orientation and the tissue of the magnetic field. Basically, there's a distortion of the magnetic field right at the boundary here. So normally, we would expect this to be 0, but we actually get this type of distortion of the magnetic field. Okay. And this is due to the boundary conditions coming from the electricity and magnetism physics. So now let's look at our frequency, the frequency versus position here during our frequency encoding step. So nominally, we'd have a frequency to position mapping like this. And so our positions along here, or let's do it the same way as before. Sorry, let's do X's. Would map to these positions. O's here, and if we were to reconstruct our image over here, we're again going to map this frequency axis onto the x-axis, and we would get a an image of our object, of our tissue here. But what happens with this distortion of the magnetic field at the boundary is that this causes a change, that this basically is added on to that. So we're going to have so normally we'd have frequency is gamma bar GXRX, but what we're going to have instead is that we're going to have this additional offset to this relationship. Now our frequency is still the contribution from the gradient, but plus this change in the Z magnetic field as a function of position. Okay, so I've taken this linear line here, I've added this little distortion on top of that. And so let's take a look at what impact we expect that to have on our image. Now, far away from the edge here, we'll have the same mapping as we did before. And as we get closer here, again, the same mapping. But now, what's going to happen at the middle point here is right next to the center is actually, it's going to be mapped up to this frequency value right here. So when we take our frequency axis, we're going to flip this over and take the different frequencies, convert them into position. This is going to cause the signal to actually spread out or stretch. And so what the actual reconstructed, so again, we're the frequency offset, we're adding some extra frequency on top of our frequency encoding gradient. Our reconstruction mistakes this for being actually existing at a different location. So we're going to get something like this. We're going to get a stretch artifact. So this distortion at the boundary sort of creates this gradual stretch. Now let's set up. Now let's flip or let's say we switched. Let's do the same setup here, where we have this distortion of the magnetic field at the boundary. But now let's invert the readout gradient. So we've just done minus readout gradient here. And we'd be choosing a different value. Let's say we just flipped it around. And we can do our same nominal mapping to frequency, and I'm adding this in here just so it's clear that now we're going to map the frequency in the opposite direction. We know we've inverted our gradient. So these 3 points in frequency map to these locations in X. Very good. We get, this is how we would normally expect frequency encoding to happen without this change in the magnetic field. But now we've got to look at the frequency versus position if we add this offset. And it's going to look something like this. So it's a distortion at the boundary here. Negative GXRX plus this function that's changing the magnetic field as a function of position. And let's take a look again at our 3 separate locations. Again, away from the boundary, there's no change. As we get closer to the boundary, you might see some, I'm just going to draw it as a little shift a little bit closer. And then right at the boundary, you're going to see the largest shift up to this point here. And so it's actually going to push the boundary. It's going to push this edge back away from where it originally is. So the frequency offset shifts our position in the frequency encoding. And then the signals are squishing up, or they're piling actually on top of each other. So we're going to get, instead of the signal stretching out, it's going to pile on top of each other, and we'll actually see an increase signal. So this is what's commonly referred to as a pile-up artifact. And these two stretch and pile-up artifacts are very characteristic of displacement due to magnetic susceptibility differences. Okay, and here's some examples of that, where you see these bright bands, for example, are examples of the pile-up artifact, and the one on the right here is a metal implant where you have a hole in the middle where the signal has actually stretched out, and then pile-up artifacts on the sides of that. Okay, another type of artifact that's more specific to chemical shift is this boundary artifact. And we've talked about a similar case in terms of when we were looking at inversion recovery, one of the examples I went through. We talked about inversion recovery is actually we can get signal cancellation within a voxel. And what happens here is we have a resonance frequency difference between fat and water. So their transverse magnetizations will actually rotate at different amounts, and they can actually point away from each other. We can have some kind of dephasing. And we have this definition of out of phase echo times that we'll use here, and also when we get into the so-called Dixon fat water imaging methods, this concept, we'll use this again there. And so you end up with a phenomenon at the right, where the top image here is acquired when, if we look at here, the transverse magnetization at a time when water and fat, and again, these are we're observing transverse magnetizations, it's when they're pointing in the same direction. But since they're at different frequencies, you can have different phase where you just say water is not changing resonance frequency. So it's always pointing in the same direction, but fat is actually rotating at different echo times. And so the bottom image, we're getting some signal cancellation in these boundary boxes that have both fat and water. Okay, so here we're going to illustrate what's happening with the chemical shift boundary problem. So the problems happen when you have a voxel that's partially fat or lipids and partially tissue, other tissue, so basically water signal. Recalling that now we've got this frequency offset for our fat. Okay, so say we come in our pulse sequence here, we do some 90-degree flip angle, tip our magnetization into the transverse plane, and if we map things over time here, and we're going to neglect relaxation, that our usual model is that, well, if we just have no change in the resonance frequency, we're just going to have the transverse magnetization pointing in the same direction. But what's happening with the fat is might be initially tipped down in the same direction as the water. Over time, due to the change in resonance frequency, it's actually going to be rotating at this difference in resonance frequency, so this chemical shift difference. And eventually we can get to a state, for example, where it would rotate to be completely out of phase. So what we want to look at here, so then in each of these cases, what is going to be the total net magnetization of our voxel? In this case, they're going to add coherently. But the next time, they're going to add slightly incoherently. So our total signal in this voxel, represented by these black arrows, is going to be reduced. And then the out of phase case is where it gets really interesting, is that we could actually end up in a situation where we have no signal. And so that's what was illustrated in the previous imaging example, where you could have these black lines at these boundaries of the fat in the water. And we'll expand upon this concept when we get into the gradient echo concepts, specifically fat water imaging, or sometimes called Dixon imaging. Okay, the next artifact is more a refresher. We'll go a little quickly through this, but this is T2 star. Recall that this is both the inherent material T2 decay plus additional decay due to the macroscopic magnetic field inhomogeneities, such as what we've discussed, magnetic susceptibility. And this can be quite large and create substantial artifacts. So typically, again, are happening in our two places where we have the biggest magnetic susceptibility differences. The example at the bottom here is a case of a metal implant, a hip implant, and we see this black signal void. This is basically really short T2 star values. And then the other examples here, shown before, are the loss of signal, particularly around the sinus canals and also near the eyes that have a big air interface, obviously at the front, and the sinuses here. A bunch of places there's signal loss at later echo times due to T2 star decay. Okay, so the next artifact we're going to talk about is like what's often called a truncation, or a Gibbs truncation, Gibbs ringing artifact. And this has to do with Fourier sampling and the fact that we're only doing sampling a limited region in K-space. And one result of that is that, especially when you have a sharp edge, you get this oscillation or the ringing artifact from these sharp edges. So you can see in the circle image here at the top, we have a Gibbs ringing in the up and down direction, which has a coarser spatial resolution, and then versus the left-right direction, we see less of that. And here's a couple examples where this can be really, problematic clinically. So here, this is originating from the high contrast in the cerebral spinal fluid and the spinal cord, and a little. There's sort of a mirrored line right next to the actual tissue boundary here. So these white arrows are showing a ringing artifact, not in fact actual pathology to be worried about. So this artifact goes away at finer spatial resolutions, or with some sort of filtering in K-space is a common way to kind of dampen it down a little bit, something called maybe a Fermi filter. So I want to explain and use Fourier theory to explain how this phenomenon arises. Okay, so what I'm starting here with is an example of just a rectangular object. So chosen this example because, like the case of Gibbs ringing, has these two very sharp edges. And this would be the idealized sampling and the idealized rect function. And in fact, this assumes that we're sampling the K-space data out to infinity, because the sinc function never completely goes to 0. So to get this perfect rect function, we need infinite K-space sampling. But of course, in reality, we want to model the fact we're only sampling a limited or finite region in k-space. And so we can model this by multiplying, in this case, the Fourier transform data, which is a sinc function, multiplied by a rect function. That this is going to be a way for us to represent the fact that we only have finite k-space sampling. And one of the Fourier transform pairs that we haven't used so far, but we'll show the result from here, is this fact that if we have a multiplication in one domain, that's shown at the left at the bottom here, we're multiplying in our k-space data, which is the sinc function, multiplied by the rect function representing our finite k-space sampling. That in the Fourier domain, so we take the Fourier transform, we're going to get a convolution, this convolution operation, denoted by the star here, not to be confused with a multiplication. And so what we're going to have is a convolution of these, the Fourier transform of these individual functions that were multiplied. So our rect object, what we hope to recover, but convolved with this, actually now a sinc function. And this is basically the non-idealities. The sinc function at the right here represents the effect of the finite sampling. So what the result of that convolution is the plot that's shown at the right. Okay, so at the left, you can see now I've cut off the k-space data at a given width, and the right is the Fourier transform of that, which now looks basically like a rect function, but we see these substantial oscillations around, particularly around the sharp edge. And this is exactly, and that's due to that convolution operation with the sinc function. And this is exactly the Gibbs ringing, or the source of the Gibbs ringing or truncation artifact. These next couple slides illustrate that as we change the extent of our k-space sampling, it modulates this artifact, so it actually becomes wider or extends further beyond the edges as we acquire less and less k-space data. And as we acquire even less k-space data, or our truncation width gets narrower, these oscillations get wider and more prominent, and this transition width, so now our sharp edge of our rect function becomes blurred out, and this is basically our spatial resolution. Okay, moving on to our next set of artifacts, motion artifacts. And motion artifacts primarily arise in the phase encoding direction because they are due to inconsistency, so motion, between our TRs. There's the motion on the time scale of an individual readout time, like tens of milliseconds, is generally quite small, but the time interval at which there's a much greater problem for motion is our TR interval, so tens, hundreds, milliseconds, seconds of time. For example, your heart is beating once a second about, right? Or you're breathing once every several seconds. And so these are the most common types of motion artifacts, are artifacts that are happening from one TR to the next TR. And we generally lump these into, and these are going to happen in the phase encoding direction. And we're generally going to lump these into two categories: periodic motion, so this is a flow, and it's coming from the heart circulatory system, or the heart itself, or some sort of regular breathing pattern. And then the second bucket of motion artifacts will talk about our more random motion. And these two examples kind of show this nicely. On the top example, this is an axial slice in the neck. And for example, a couple of these bright features are blood vessels. And you see these little ghosts, repeated bits of this blood vessel over here. And so this would be a periodic artifact that leads to these these are what we're going to call ghosts. And the random motion, like this person moving their eyes, maybe blinking a lot, gives this more diffuse. You can see a little bit of ghosting pattern here, but it's much more of a diffuse artifact. But other common causes of this are irregular breathing or coughing, a sort of bulk motion system, you're just shuffling around in the scanner. So here's how we're going to model this motion. I'm just going to propose use this simple model for the data. So let's consider just a point, the object that we're imaging is just a point source or a delta function. So we have our Fourier transform relationship to k-space. Actually, why don't I k-space, which now let's remember this is in the ky, so this is our phase encoding. These are these discrete samples here, but it's basically at this constant amplitude. It gives us the delta function. And if we look at the data that we're acquiring in time as we're moving across these different phase encodes, this would be this constant amplitude data. Now the way that we're going to model periodic motion is that it's some additional signal fluctuation. Like for example, the tissue is moving from one voxel to an adjacent voxel, or a blood vessel may be getting brighter or darker due to the amount of blood flowing through it, or expanding or contracting the size of the vessel, or you're breathing up and down, again shifting tissue. So we're going to model that as this periodic oscillation on top of our signal. So maybe first TR we get the same data, but now as we go from TR to TR here, we get some periodic oscillation. And so when we take our data over time and we put it into k-space, we're going to see the same pattern. Some oscillation in k-space. So we can generally represent that as for this point object case is the normal data plus some term representing the oscillation. And for simplicity, we're going to say this is some cosine function. And we'll say it's at some motion frequency across k-space, for example. Or this could be a sine function, and you'll see that any sort of periodic function we add on here is going to lead to our ghosts in the Fourier domain here. So what we should expect to get in our Fourier transform domain is we get a copy of what we want, our original object, but on top of that, we're going to get these ghosted copies. So recall that the Fourier transform of a cosine is, and let's add a scaling factor here too, because it's not going to be usually not going to be the same size, right? It's some smaller oscillation on top of a bigger signal. And we could easily put a sign in here. It's just going to change the real and imaginary components of this. But what we're going to get is these two, in this model, okay, of the motion, which is an approximation, but we're going to get these two extra functions out here. These would be at some values in this case. And these are going to be our ghosts. And so they're coming from a single source. They have these very distinct locations. If we knew, for example, we knew our k-space coordinates and the time, the tr it takes, we could actually determine what we could actually calculate out what these specific locations we would expect these ghosts to appear at. But this is the theory that's going to support in principle, and you can go do a little more complex model, make this cosine sort of an arbitrary periodic function, but as long as it's a periodic function, you'll see these repeated ghosts in the image. Now the case of the random signal modeling, I'm going to start with the same situation. Let's look at and this is a type of what's called point spread function analysis, when we're just looking at the response of from a delta function. So if we have some more random fluctuations on top of our data, then we're not going to be able to sort of have as clean of a motion model, but we have some motion, some function that modulates the motion. And when we go into our Fourier domain, we're still going to get a copy of our original point object here, but then can use our lowercase and uppercase Fourier notation here. So this is simply the Fourier transform of whatever this random motion function is. If one thing actually says is if one part of Fourier theory you can take is if f motion is some this basically says it's like white noise, Gaussian noise, then the Fourier transform is also going to be white Gaussian noise. So what does that mean? We'll get our original object here, but we're going to get some noise, and this is what we're referring to as this like diffuse artifact here. And remember, this is happening specifically in the phase encoding dimension, because we're saying that motion is a problem in the longer time scales, so across the experiment. So here's a couple examples. The bottom right would be a motion-free image, an axial slice taken at the top of the liver with a little bit of the lungs in there. On the top left, you see a periodic motion artifact from pulsatility in the descending aorta here. And on the top right, this is a similar location in the abdomen, and this is a respiratory motion artifact, a little bit more less periodic, or maybe some irregular breathing. So you get some semblance of like these periodic ghosting features here, but a lot more of a diffuse artifact. And then pointing out these are the ghosts originating from this signal source right here. So there are a number of ways to solve this. Gating to the cardiac respiratory cycle, breath holding, flow suppression or flow compensation, topic that's addressed later in the textbook, spatial saturation, also addressed in the tissue suppression techniques chapter, or this is an artifact in the phase encoding direction. So if, for example, we can accept that this is going to be an artifact, but we could say try to push the artifact in a direction that's not going to impact the structures of interest. Okay, I'm quickly going to cover the so-called magic angle effects. So this is a sort of a interesting artifact that what happens is that highly ordered structures, so this is most common in tendons and ligaments, which actually typically have really short T2 values, so these would be T2 or less than 10 milliseconds. That when these tissues are oriented at a certain angle with the relative to the magnetic field, and this is the so-called magic angle, the relaxation time, their T2 value will go up substantially. And the magic angle turns out to come from the pattern of a magnetic field generated by a spin, by a dipole, and it's going to be this angle right here, 54.7 degrees, where this is the direction of the B0 field. Similarly, this is the direction of B0 field in this image. And as this tendon is coming down, you can see like right in this part of the tendon, it now it's at approximately this magic angle. So this is common in tendons and ligaments and can be confused for normally these, like this tendon is normally dark because the T2 is so short. The tendon T2 is more like 1 millisecond. Ligaments are a little longer. So you'd expect it to be black if you see signal in there. That maybe means some fluid accumulation or something, but if you see signal in there but the tendon is oriented at the specific angle, then it could be a magic angle effect. Okay, another type of artifact I'm going to cover is RF interference, or sometimes called zipper artifacts, for the appearance that you can see in the images on the right. And this is some sort of radio frequency contamination. It can be the transmit RF leaking into the receive signal, or it can come from external sources of RF signals. And this appears that as an extra signal at a given frequency encoding location. So if we draw our picture of frequency encoding here, and let's say You know, uh-oh, somebody left the door to the magnet room open, and coming from the outside world, there's a little bit of extra RF not coming from us creating it for the purpose of the experiment. This can even happen in components inside the room. I've heard of this happening with light bulbs. So if this RF comes in here and it has, say it has, you know, some frequency, and let's call it frequency zip for zipper. What's going to happen is when we decode this frequency encoding, so basically when we map the frequency back to position here, we're going to get an artifact at a very specific location in our frequency encoding direction. You know, in this example here, you see it appears at a very specific location in frequency encoding, suggesting it's a single frequency. This image has like a range of RF interference. Creating this band of artifacts. So there's shielding built into the rooms to prevent this, keeping the doors closed, or if it's an RF coil leakage issue, then you got to fix those RF coils. Okay, getting through a lot of artifacts here. So next we're going to talk about a couple of gradient artifacts. First we're going to talk about is eddy currents. And what these basically do is usually we're trying to apply some gradient. And so we have some ideal trapezoidal shape that we're using. But eddy currents are currents that exist within that are created, in fact, in parts of the MRI system. They can be created in the B0 magnet. They can be created in other coils. They can be created in some of the shielding. And what happens is that we have some ideal gradient that we think we're playing, but in fact, the actual gradient waveform, well, takes a little bit of extra time. It kind of overshoots maybe the intended value, and then maybe something like this. So, for example, what could happen if this was not accounted for would be you'd expect to acquire a case-based line here. But for example, this mean things are a little bit lagging, so you'd actually not acquire the same location in case space, but you think you've acquired a different location. This turns out to be a much larger problem for fast imaging trajectories like echoplanar imaging that we'll talk about in a couple of weeks, as well as non-Cartesian trajectories like spiral or radial imaging. And the corrections that are built into the scanners, these eddy current, so-called precompensation, are based on measurements of these, and these are generally pretty good. Now, another type of gradient artifact is gradient non-linearities. So what we want our gradient to do is what I'm going to draw here in the blue. We want our gradient to create this change in magnetic field as a function of position. But in reality, at some point, the gradient coils end, and the gradient coils no longer become linear. So usually they're linear, you know, over some nice range in the middle here, but then this linearity flattens out at the edges here. And so let's remember here that this delta Bz, the frequency is in fact gamma bar times this delta Bz. And so we're using this for spatial encoding or slice selection. So we might think that, and this becomes a problem way at the edges here, is that at a certain position, if we have linear gradients, we expect to measure this frequency value. So when we reconstruct an image, you know, you would expect when we take this frequency, right, we map it back to position here, we would expect the signal to be here, and similarly on the other side here. So we might expect to get our object that looks like this. But this non-linearity, and typically the way it works is we're going to get this compression. So if we look at where the actual frequencies of these locations that are up at the edges here, the actual frequencies are going to be lower than we expect. So when we map them back to position, they map to lower positions than we expect. So it actually leads to this also sort of a compression. A little bit distorted there, not intentional. But we sort of get this compression or distortion of the object that you can see quite clearly at the edge of these images. And keep in mind, these are very large field of view images. This is like a whole abdomen. So when you get to the edge of these gradients, and you can do a pretty good job at correcting for these by measuring the nonlinear magnetic field. So this red line, we would actually measure this and then apply what's called a gradient warping correction. Okay, and we're here at our last artifact. And these are dielectric shading effects. So the problem here is the RF waves actually have some finite wavelength, meaning they don't perfectly propagate through our entire body in sort of a uniform fashion. And that's illustrated. I stole this this wavelength slide from chapter 2, where the wavelength of our radio frequency waves gets shorter as we go to higher and higher magnetic field. And as this becomes shorter, we become more susceptible to these shading, this dielectric shading effects. It's called the dielectric shading because it's the dielectric constant that determines how RF propagates through the tissue. So, you know, at 3 Tesla, this wavelength is 26 centimeters. Most of us have a dimension that's bigger than 26 centimeters, so we can certainly see this artifact. And this picture here in the bottom left from the textbook is a 3 Tesla image, or you can see a dark band there corresponding to this dielectric shading effect. And there are some simple image-based corrections that are often applied to try and reduce this. Here's a couple of resources. The top, hopefully one of my and one of your favorite websites, MRIquestions.com, has a huge section devoted to artifacts, very thorough, very good resource. The bottom link there is from a journal called Radiographics, which is an educational journal for radiologists. Both talks a lot about clinical questions, but also technical considerations as well. Okay, so we covered a lot of ground here, a lot of different artifacts, some of which we'd seen before, like aliasing, but some key new ones. I think, so it's aliasing, we covered off resonance, and this is due to both chemical shift and magnetic susceptibility. The artifacts arising from this, like displacement artifacts, are a very important one. This boundary problem partial volume effect due to chemical shift. And we also looked at this previously in inversion recovery. Truncation and Gibbs ringing, motion artifacts. Then a couple less common ones, magic angle and crosstalk, which we had mentioned in chapter 10. We showed the RF zipper and T2 star artifacts that are quite common. And ones that are pretty well corrected for by the system are the gradient related artifacts. I didn't go through them here, but we did in chapter 13, went through like errors in the data like spike artifacts. And then finally mentioned the dielectric effects, so image shading that you get from that. Okay, thank you very much for watching.